Okay, so for today, I'll be talking about the quantitative analysis. And for quantitative analysis, it's the follow-up of your salt preparation. In salt preparation, we saw three main types of salt preparation techniques. Number one, your crystallization. Number two, crystallization. Number two, we have your titration. And number three, we have your precipitation. And this is dependent on the type of salts that you are creating. Are they soluble salts or are they insoluble salts? So if they are soluble salts, we usually use crystallization and titration. For insoluble salts, we use precipitation. And what segregates crystallization from titration is the reactants. Are they all soluble? If all are soluble, then use titration. If it's insoluble, for the reactants, use crystallization. And most of it hovers around the three general word equation for acid-base reaction, which is metal plus acid will give you salt and hydrogen gas. Carbonate plus acid will give you salt, water, and carbon dioxide. And of course, lastly, neutralization reactions, which is salt plus base to give you salt and water. Okay, so for quantitative analysis, there is a few ways to study it. First of all is to recognize the cation and then to recognize the anion. So there's a series of tests and definitely the test of the identity of the gas. The identity of gas helps you to understand what are the reaction type that actually underwent, and more importantly to actually see whether is it a carbonate or is it an ammonium salt. For the then what's the difference between a cation and anion? Because for salt, right, salt is generally made up of two main things: your cations and your anions. So we will be able to do a quantitative test to identify what is a cation, and then we will do another test to identify what is the anion. And through this combination, we will then be able to identify what is the name of the salt. Okay. So what is this quantitative analysis? It is the process in which we use to identify the cations and anions in an unknown solution. As most solutions they tend to be colorless. Okay. Now how do we go about testing for cation? We can use two chemicals so far. Number one, we can use either sodium hydroxide, which is NaOH, or aqueous ammonia. Okay, and the thing is, after we have added either these chemicals, we will want to add in excess to double confirm what the identity of the cation is. So step one. So the first step is mainly test with aqueous sodium hydroxide or aqueous ammonia. Okay. The second step is to add in excess the respective item that you use. No, you don't have to use both sodium hydroxide and aqueous ammonia. You use one and then you add in excess. So most of and what's the value of this is that you will be able to produce your precipitate, and with precipitation you can actually see colors lah. Even if it's a white precipitate, the confirmation test of adding that excess of either aqueous sodium hydroxide or aqueous ammonia gives you a kind of indication. Okay, so what will happen is the color of the precipitate will be produced, and whether it will be either soluble in excess or insoluble in excess. That means you add extra more. And subsequently, you will then can test for ammonia gas. Okay, if you add sodium hydroxide to test to see if the solution is an ammonium salt. Do note that it is not recommended to use aqueous ammonia to test for any form of ammonium salt for the cation. Okay, so that's one thing to note. So what is the precipitate form? The precipitate form usually is actually the hydroxide of the metal ion, which is the cation. This comes from the cation. So when the cation forms together with the hydroxide, okay, you will then form a precipitate, and this precipitate generally gives color. One good example is your copper 2 plus ion, which were reacted with hydroxide will actually form copper 2 hydroxide. Okay, where do they get the hydroxide? They get it from aqueous ammonia. Not aqueous ammonia, sorry. Aqueous ammonia and aqueous sodium hydroxide. So both of it. So aqueous ammonia is not NH3. That's not the chemical formula. But aqueous ammonia is um, the combination of water together with ammonia gas. Okay, so over here, this is where we can see the color change from an unknown substance. You actually add either aqueous ammonia or sodium hydroxide to produce your light blue precipitate. And when you add in excess, okay, when you add in excess of sodium hydroxide, it will tend to be insoluble. Okay, the precipitate will still be there, and most probably it will darken. You have a darker blue precipitate form. On the other hand, when you look at aluminium, you will produce a white precipitate. However, when you actually add excess sodium hydroxide, you will actually be able to dissolve. That means the white precipitate will be dissolved. So what is the general amount they add? You tend to add maybe a few drops, like five drops to 6 drops, to actually see what is the precipitate form. You can consider to add more. However, when you add in excess, literally you fill your test tube by maybe another 2 cm cube of the volume more only lah, and you shake. Okay, do remember to shake. So in this case, for a new test form, that's where if it's dissolved, you may want to confirm it with aqueous ammonia to see whether the precipitate will be still insoluble. Generally, we tend to do two of these. First sodium hydroxide, then aqueous ammonia, in the event it is white precipitate, to further confirm it. Okay. So some of these precipitate can dissolve because they actually form soluble compounds when in excess in either of the chemicals. So for example, you might be tested, let's say this cation, what is the precipitate form and what is the color form. Okay, and do take note, you can actually form a deep blue solution when dissolved for aqueous ammonia, but not for aqueous sodium hydroxide. Okay, so what are some of these tests for all the common cations when they react with sodium hydroxide? We could see that for zinc, aluminium, lead, and calcium, they all produce white precipitate only after a few drops. However, when you add in excess, right, you would see that it further distinct, whereby the precipitate dissolve in excess for zinc, aluminium, and lead. However, it doesn't do it for calcium. So this is how you can confirm that when in excess it is and the item or the precipitate is insoluble, it is the identity of the cation is actually calcium. However, if it still dissolve, just like your zinc, aluminium, and lead, then you will need to consider adding aqueous ammonia. Okay, other colorations to consider, right, is like copper 2 plus, which is light blue, iron 2, green precipitate, 3, iron 3 is actually reddish brown. So this one, there's a distinct difference. And of course, ammonium, you will not have any precipitate. However, you will produce ammonia gas. For cation wise, right, when you use aqueous ammonia, you would see that all of it will produce white precipitate except calcium. So calcium generally you will not have anything to react with your aqueous ammonia lah. It's not that it doesn't react, it's just that there is no precipitate form. However, when you add in excess, you could see that for zinc it still continues to dissolve in excess. However, the aluminium and lead, it is insoluble in excess. So it can be either aluminium, it can either be lead. And more importantly is if we can use aqueous ammonia to distinct zinc from the rest. Okay. So copper 2 plus, when you use aqueous sodium, this one is not sodium hydroxide, this is a typo here. It is aqueous NH3. Okay. No, I think there's a mistake. Okay, for the summary of test for aqueous ammonia, um, we will double check and I'll get back to you on this. But moving on, what will happen is it should be something like this, where for sodium hydroxide, you will actually be able to produce a green precipitate, reddish brown, and no precipitate, only in a few drops. So this carries all the in a few drops. Okay, whereas in excess, what are the different changes? It is as stated below. Okay, so for ammonia, you could see that in excess, it will actually produce a deep blue solution. Do we have a deep blue solution? Yes. So this one should be. Then iron 2 ion will actually form a blue precipitate. Yes. So in this case, the only mistake is this typo. So for testing with aqueous ammonia, on adding a few drops, you get actually a light blue precipitate. However, this precipitation will dissolve in excess aqueous ammonia, forming a deep blue solution. For iron 2 and iron 3, you could see that the color is still the same and that this precipitate is not in is actually still insoluble. That means you will still be able to see the precipitate and its color. So no much change will occur when you add in excess. So these two tables is something that you have to remember. Okay, for now we move on to anion, which is the second part of the salt. So for anion, right, there are a few common anions that we tend to use. So in our acid-base chapter, right, you have your carbonate that will produce your carbonate ion. You have your nitric acid, which is HNO3. It will actually generally produce your nitrate ions. Then you have your chloride ions generated from hydrochloric acid, and you have your sulfate ions that is generated from your sulfuric acid. So you could see that these are the common kinds of ions that you have to remember, and it's mainly because of the chapters that we have studied before. So for carbonate ions, right, one very simple way to test is the production of the gas carbon dioxide, which actually will be able to turn your white precipitate, if you're actually able to form your white precipitate from your lime water lah. Okay. Secondly, for nitric ions, right, you will want to add sodium hydroxide so that and as well as a piece of aluminum foil. So when you warm it, right, the gas will actually release. The gas release is actually your aqueous ammonia, and it will actually you can actually test it with your a piece of moist red litmus paper. So your moist red litmus paper will actually turn blue and further confirming that it's actually a nitrate anion. For sulfate, very simple. You just have to add nitric acid and barium nitrate. The purpose of the nitric acid is to remove the sulfate ion so that when barium actually is being released and is able to react with the sulfate ion, it will then be able to form a white precipitate. This one do not require any test of gas. For chloride ion, you use the same concept, but rather than using barium nitrate, you use silver nitrate. Okay, and this will actually cause a simple displacement reaction, such that the chloride ion will actually remove the nitrate and it combines with silver, forming silver chloride. This is a very common exam question which you need to know why the white precipitate is formed, or you might be required to write the chemical equation of the formation of silver chloride. Okay. Finally, we use iodide, which forms an ion, which will actually is another cation. However, this unique thing is that rather than it being white, it's actually a yellow precipitate of silver iodide being formed. If you remember, the original color of iodine is actually very very dark. Usually it's like purplish or yellowish purplish kind. So this reaction will give you a tinge of yellow precipitate. So for the anion, we are looking at this, where for if you want to test for carbonate, we will react the carbonate with an acid, which will be able to form salt, water, and carbon dioxide gas. Then we test for the identity of the gas, which is CO2, with lime water. Then of course, when we look at the the ammonia gas or the nitrate anion, we want to test for the presence of ammonia gas, and this is done with the use of aluminium foil. Okay, and then of course you react with sodium hydroxide to release the ammonia gas. Then when we look at the sulfate chloride, these two will generally produce white precipitate. However, for sulfate we use barium nitrate. So the white precipitate is actually barium sulfate. However, for the other one, we actually have test for chloride, right? So we use nitric acid with silver nitrate, and the white precipitate will be formed is your silver chloride. The other one would be when you test for iodide, it will be your silver iodide, so AgI. So this AgI, the yellow precipitate. This will be AgCl, and this one will be barium sulfate for the white precipitate form. Okay. Then, how do we identify the gas? This gas is usually released when there's actually a chemical reaction. So you should be able to see an effervescence. If not, sometimes some of these gas there is color or there's a smell. However, for the ones that you do in the science lab, they tend to be colorless. So you can't really tell the color. However, you will be able to see, you'll be able to smell something if it's ammonia gas. And if it's a solid substance, you tend to heat them up. So when we look at hydrogen gas, they are usually colorless and odorless. To test this, we use a lighted spleen. Now, there's a difference between lighted spleen and later on you'll see glowing spleen. So for lighted spleen, it would have a flame at the end of it, of the stick. And this flame will then, in the presence of the gas, will be able to extinguish your pop sound. In other words, like a mini explosion. But you can only write extinguish with a pop sound. So when in contact with the gas, it will then pop. And that's why we don't use glowing spleen, because glowing spleen is not as strong as the one with flame. However, for oxygen gas, we tend to use a glowing spleen. So a glowing spleen is something like the joss sticks. If not, it's something like the cigarette, whereby after you light it, you heat it up, it burns a very bright orange color. And this bright orange color will then stay there, but there will be no flame. And what will happen is when it is exposed to an area with oxygen, there will be a rekindle of the flame, forming a mini fire or flame. Okay. Next, we look at carbon dioxide. So for carbon dioxide, right, it's also colorless and odorless, where it can actually bubble the gas through lime water. So what will happen is you'll form a white precipitate, and this precipitate will actually dissolve upon further bubbling. We look at chlorine gas. Chlorine gas, this is the only one with the color in your syllabus that you need to know. It tends to be a greenish yellow color. However, there's a pungent smell to it. And how to test for it? You put a moist blue litmus paper at the mouth, and generally it will bleach away, um, meaning it will actually turn like colorless or white color. Reason being, chlorine is actually a natural bleacher. Okay, usually like when you wash your school clothing, when it's white in color, you will tend to want to use it to remove any stain. Then we have sulfur dioxide that is colorless and but has a pungent smell. So for this, what we do is we tend to soak the filter paper with acidified potassium manganese. So do take note that this one is not your litmus paper. Now, what is potassium manganese 7? This is actually an oxidizing agent. And an oxidizing agent basically is an agent that oxidizes something but gets reduced by itself. And what happens is for potassium manganese 7, it is actually purplish in color. So after it has undergone oxidation, it tends to actually turn colorless. So what happens is when exposed to sulfur dioxide, it will actually oxidize sulfur dioxide and get itself being reduced. Ammonia gas, this one is very common. It is colorless with a pungent smell. And by placing a piece of moist litmus paper at the mouth of the test tube, This moist litmus paper would actually turn blue. Okay, and of course the smell is very, very smelly as well. So furthermore, this is the summary chart of how we can identify the gas, whether is it odorless or pungent, and definitely what are the different categories of it. The most common one that usually is tested is actually the ones that I highlighted. These are the ones that you will tend to see more often in your exams as well as in your practical. There's another test for the presence of water, which is hydrated. So hydrated salts are basically salts that contain water content. And water tends to be colorless and they are able to condense at the mouth of the test tube. So how do we test? We actually use anhydrous chloride. This one can be in a solution form or in a present on the filter paper. So what happened is this water will actually change the color of the cobalt 2 chloride paper from blue to actually pink in color. And you can actually test it with anhydrous copper 2 sulfate. Okay, that's another one. In which right the water will change the color of the anhydrous copper 2 sulfate from white to blue. So these are the two other tests that you need to be familiar with. And then these two tests only shows the presence of water. It doesn't tell you how pure the water is. Whether is there impurities or what's not, you can't tell. Okay, so generally that's the main component for quantitative analysis. And if you want, you can always review the previous video on salt preparation. Thank you.